Thank you.
Thank you very much for the invitation, and thank you for your interest in this field of research. Yes, I used TUBALL tubes or single-walled carbon nanotubes for the preparation of polyamide 6 nanocomposites, and the actual compounding step was carried out by an in-situ polymerization. All right, let's start about my background. I'm working for Lehmann Voss, the business unit Customized Polymer Materials. We are a globally operating organization with facilities in North America, Europe, and Asia. And we are specialized in tailor-made materials. So that's why we are always interested in new, advanced, or high-end filler materials like TUBALLs or graphene or other nanomaterials. All right, so I'm working in the project where my goal is to find new ways to achieve an electrically conductive polymer material with superior properties in terms of mechanical features and price. Because a well-known problem is if you want to make a conductive composite, you have to add conductive filler material. But the problem is the material gets brittle because all of this filler. So the flexibility decreases, and if you using pricey nanomaterials, the price will increase. And so my task here was to find a solution for this problem. Let's have a look at the commonly used filler materials. The most obvious one is metal in the shape of powder or metal fibers. But also lots of carbon fillers are used, or carbon-based fillers, such as graphite, carbon fiber, or really famous here, carbon black. For some special application, it's also common to use semiconducting powder. Let's have a closer look at one of the cheapest conductive fillers you can get. It's graphite. Graphite is built out of sp2 hybridized carbon atoms, which forms honeycomb layers, and these layers are stacked with a distance about 300 picometers. So this is graphite, it's pretty cheap. And when we isolate one of these layers, we got graphene. And so this looks pretty easy, this isolation, but in fact it took until the year 2004 for the successful isolation or exfoliation of graphene, and this experiment was decorated with a Nobel Prize. So nowadays we find that it's kind of a gold rush for graphene, because graphene, it's supposed to be the strongest material in the world. Professor Hone from the Columbia University said it will take an elephant balancing on the pencil to break through a sarin wrap of graphene. What does it mean in numbers? Graphene has an E modulus of about 1 terapascal and a tensile strength about 120 gigapascal. So it absolutely outperforms construction steel about 100 times. But also in conductive matters, graphene has really outstanding properties here. It has an electrical conductivity of 10 to the power of 8 Siemens per meter, and thermal conductivity about 5,000 watts per meter in Kelvin. So here it outperforms one of the best conductive metals, silver, about 10 times. And we can imagine out of graphene, we can imagine other nanostructures like carbon nanotubes. If we have a single layer of graphene and we wrap it up, it will leads us to a single-walled carbon nanotube. If we have several layers of graphene, called multi-layer graphene, we wrap it up, we get a multi-walled carbon nanotube. So what is a bit counterintuitive here is that the less layers you have, the better the performance is. So the best material you can get is a single layer graphene or a single-walled carbon nanotube, such as TUBALLs here. And I can tell you, I worked with all this material, with graphene, multi-layer graphene, multi-walled carbon nanotubes from different suppliers, but also with TUBALLs, and I can tell you, the TUBALLs, I get really the best results out of it, so it's outstanding here. All right, and this this carbon nanotubes have similar properties of graphene because it's basically the same structure and it's so related to. Yeah, so now we see the white rabbit here took us really far into what I call the nano wonderland, because it's promising so nice properties for everything, and it should be a solution for everything, but in the real world it appears just as a black powder. It's not a real construction material, it's just black powder with a maximum dimension of several micrometers. So the question is, how do we transfer these properties, or some of these properties, to the real world? And the answer is already given in my title, so let's make composites. In my case, I took PA6 as a matrix material. So PA6 is one of the most used construction polymers in the world. So it's widely used and pretty cheap. And here is what we are doing. So the state of the art for compounding today is to use an extruder to melt the polymer material and mix it with the filler. In this case here, I used an extruder and carbon nanotubes and to change the property profile of PA6. We can see here the profile, the mechanical properties with E modulus, tensile strength, elongation at break, but also the electrical conductivity and the availability as an inverted price. And we see PA6, it's quite cheap, it's quite ductile, so we can make fibers out of it, but it's also an isolator. And now let's see what's happening when we use an extruder to incorporate TUBALLs here. With 0.05 weight% of TUBALLs, we directly get here an effect to the polymer material. The elongation decreases and the E modulus increases, also the tensile strength is increasing. Just, you see here. This is, for me, it was remarkable. Just as such a low filler grade with an extruder to have such a big effect here. And if we keep it further, the effect will go stronger and stronger. And now we have to take into account that the costs will be increased because these TUBALLs are still kind of pricey comparing to polyamide 6. And we also see that the electrical conductivity is increasing really slowly. And just as in 1% of the incorporation of 1%, we break through the percolation threshold and achieve a really nice electrical conductivity, a high E modulus, high tensile strength, but we have two weak spots here in this diagram. It's the availability and the elongation at break. And this was my task to find a solution here. And my approach was to use a different incorporation technique. Not an extruder. I was using the in-situ technique. That means I'm introducing the nanoparticles to the polymer's cradle, so to the monomer. In the case of PA6, I mixed single-wall tubes, TUBALLs, with epsilon caprolactam. So you can melt epsilon caprolactam at 70 degrees, and it's basically a liquid like water. So you can imagine there's pretty nice possibilities for mixing and dispersing it. And afterwards, you polymerize it in this lab scale reactor here, up to 5 liters. The chemistry behind it is quite simple. It's a ring opening polymerization, so it's nice to handle. And we got this composite material here in one step. So no further compoundation is needed here. And let's have a look at the product of this in-situ made TUBALL PA6 compound. Here is an SEM picture, and we can see that we have all these tiny lines in the polymer matrix, these white lines, the really small one, not the big ones. The small lines, this network here, is formed by TUBALLs over the entire polymer. So, and we can imagine that this will have really a big effect on the property profile of the material, and this is what we want to achieve. So let's have a look at the rheological behavior of the material. So these are results from a dynamic oscillation experiment where a mechanical frequency is applied to the molten polymer, and we see in black it's neat PA6, and then we have an increasing filler content. And we see that the slope of this curve are decreasing with increasing filler content, and we also see that we have a rubber elastic plateau at the low oscillation frequency. And this is an indication for a cross-linked network, and this is pretty nice because we just saw the network. We have an optical proof of percolation here, and it's perfectly matching with this theoretical experiment here. Let's go a little bit deeper into the rheological behavior of the material to show you how big the effect is. What we see here is the oscillation frequency against the storage modulus and the loss modulus, and on the right scale it's the viscosity. And let's start with the viscosity of PA6, so it's the non-filled symbols here. PA6 behaves like a Newtonic fluid, basically. And with 0.25% of TUBALLs inside it, incorporated with in-situ techniques, it behaves like a compound. It behaves like a cross-linked network. So it shows a shear thinning effect. The viscosity is now dependent on the shear force. And we also see the storage and loss modulus of PA6 is really different to each other, but with the incorporation of TUBALLs, now the storage and loss modulus are already a little bit matching each other, and we have a crossover point there on the top. And this crossover point comes down to lower frequencies with an increasing filler content until it's entirely matching each other at 0.75%. This is where we have over the entire frequency a solid state behavior of the material. So the nanotubes are on this point really dominating the flow property profile of the material. All right, let's have a look at the mechanical properties of the in-situ made composites. We have here the filler content. I worked in concentrations from 0.05 to 1 weight%. And on the left axis, we see the E modulus, on the right axis, the tensile strength. And the bars are related to E modulus and the boxes to the tensile strength. And we see we have an increase with the filler content of both. And this is, yeah, pretty much what we expected, but the effect is really strong. It's almost 3 times higher with 1% of TUBALLs. What is happening with the elongation? It's decreasing with the filler content. This is what we expected, but the decrease, I have to say, it's not such dramatic. We still have a really, really good flexibility comparing to the extrusion compounds. And especially if we compare this flexibility with the electrical conductivity of this product. What we see here is the filler content against the specific conductivity. And even with 0.05 weight percentage TUBALLs, we see we have an increase, a significant increase of electrical conductivity, and the percolation threshold is crossed about at 0.1 to 0.2%. So this is pretty nice. And we also reach a level of conductivity where we can say this is a real this is a real conductivity. So we can build up electrical devices out of it. I just built one by myself. So it's this one here. Oh. Okay. It's this one here. So where current flows through the polymer material. Actually, it's the same 1% in-situ compound here, and it's light up this LED. So this is not just numbers. For those of you who are not familiar with it, it's working. And so it depends now what you want to have. If you want to have a product with a good elongation and anti-static behavior, you can say 0.1% of TUBALL is enough, we still have an outstanding elongation break and an anti-static behavior. If you want to go into the conductive area, you have to use maybe 0.7%, and you still have an elongation above 50, which is a great value here. All right, comparing to the extrusion compounds I showed you first, we have this curve in terms of conductivity. This is a logarithmic scale, so the difference is huge. There's a big benefit of this in-situ technique, you can see. The extrusion compounds are about 1 to 2 decades below, performing 1 to 2 decades below the in-situ compound. And for those of you who are not familiar with compounds at all, let me show you how much of a macroscopic filler you need to reach with an extruder anti-static behavior, such as conductive graphite here. We are talking about 15 to 20% to just reach an anti-static. So this is, even if you use an extruder with the TUBALLs, it has really a high performance, I have to say. All right, just one of the last slides, my conclusion here. So this is the property profile of PA6. And now I want to compare it with the property profile of this extrusion-made PA6 TUBALL compound. So we can increase the conductivity, tensile strength, E modulus. That's fine, and we can do it today. Everything is available. TUBALLs are available on an industrial scale, and we do have the extruders. But to unleash the full potential of the TUBALLs, we should use this in-situ technique and get with the same amount this property profile. And the nice thing is, even the in-situ polymerization is more sustainable because we can skip the compoundation step. So it's all in one. We have to synthesize the polymer anyway, and we just add this, this nanofiller material and get a really energy-efficient, high-performance compound here. All right, so far, thank you for your attention.
Thank you very, very much for this interesting presentation. Are there any questions from the audience?
Joachim Möschel of Feeds Company. Thank you for this nice lecture. Are your in-situ PA6 modified by single-wall nanotubes? Are these materials thermoreversible, injection moldable?
Yeah. It's still a thermoplastic, and all these samples I prepared for the testings were made by injection molding.
And did you research this material by injection moldable?
Yeah, we already processed this with injection molding and did all the samples for the testing machines.
Okay.
Thank you. There is one more question here.
In one of your slides, the 13, you showed the electrical conductivity with 5% content.
Yeah.
And what is happening with the modulus when you leave? It looks like you have.
Again? Yes.
Yes. It looks like you have the percolation point, I believe, between 0.75 and 1.
Yeah, it's true.
And what's happening with the modulus when you go to 5%?
To 5, okay. There, I have to say, I wasn't able to process the 5% material in the injection molding because the viscosity was so high. I used the 5% just for the determination of the conductivity, and also I used this 5% material for a master batch. Yeah, but it wasn't processable in an injection molding.
And do you have experience in, here you show with PA6?
Yeah.
Do you have experience in high performance polymers like PEEK, PPS, and what will happen?
Unfortunately for this in-situ method, it's just PA6 for now. Okay. Because the synthesis of PEK or other are pretty challenging.
Okay, Thank you.
Thank you very much. I assume that if you have any more questions, you can ask those questions in the lobby or during the meal. Thank you for this very, very interesting presentation.
Thank you very much.
Thank you. Thanks.